Download this code from codegive.com, link in the description below. OK, let's dive into the augmented dickey-fuller (ADF) test for stationarity in stata. This is a crucial concept in time series analysis, and I'll provide a comprehensive tutorial with detailed explanations and stata code examples. 1. Understanding stationarity. Before we get into the ADF test, it's essential to understand what stationarity means. Stationary time series. A time series is considered stationary if its statistical properties do not change over time. Specifically, this means constant mean. The average value of the series remains roughly the same, regardless of the time period. Constant variance. The spread or variability of the series around its mean remains consistent. Constant autocovariance. The covariance between values at different points in time depends only on the lag, the time difference between the points, and not on the actual time points. In other words, the pattern of dependence between observations separated by a certain number of periods should be stable over the entire series. Why stationarity matters. Many time series models, like ARIMA, VAR, regression models with time series data, assume that the data is stationary. If you apply these models to non-stationary data, you can get spurious, false or misleading results. A common example is spurious regression, where you find a statistically significant relationship between two unrelated time series simply because they both have trends. Non-stationary time series. A time series that violates one or more of the conditions for stationarity is non-stationary. Common types of non-stationarity include trends. A systematic upward or downward movement in the data over time. Seasonality. Regular, predictable patterns that repeat over a fixed period, example monthly sales that always peak in December. Unit roots. A specific type of non-stationarity where past values of the series have a persistent effect on future values. This is what the ADF test focuses on. 2. The augmented dickey-fuller (ADF) test. The ADF test is a statistical hypothesis test designed to determine if a time series has a unit root. The presence of a unit root suggests that the time series is non-stationary. Hypotheses. Null hypothesis, H0. The time series has a unit root, i.e., it is non-stationary. Alternative hypothesis, H1. The time series does not have a unit root, i.e., it is stationary. Test regression. The ADF test is based on estimating a regression equation. The form of the regression equation depends on what you want to include in your model, example whether you suspect a trend or just want to test for a simple unit root. Here are the common variations. Model with a constant, drift. Model with a constant and a trend. Model without a constant or trend. Where y_t is the value of the time series at time t. Delta y_t is the first difference of the time series, y_t, y_t1. Differencing is a common way to try to make a non-stationary series stationary. y_t1 is the lagged value of the time series, one period back. Alpha is a constant, drift. Beta is the coefficient on the lagged level variable. This is the key coefficient we're interested in. If beta is significantly negative, it suggests the series is stationary. Delta is the coefficient on the time trend, t. T is the time trend. Sigma, gamma underscore I delta y underscore ti, is the sum of lagged first differences of the time series. These lag differences are included to augment the Dickey-Fuller test and account for serial correlation in the errors. The number of lags, p, is a critical choice. Asterisk epsilon underscore t is the error term, assumed to be white noise. Asterisk test statistic asterisk the ADF test calculates a t-statistic for the coefficient beta in the regression. This t-statistic is then compared to a critical value. Asterisk however, the critical values for the ADF test are not the standard t-distribution values star. Instead, they are based on the Dickey-Fuller distribution, which is a special distribution specifically for this test. Asterisk decision rule asterisk. Asterisk if the ADF test statistic is more negative than the critical value, i.e., the absolute value of the test statistic is larger than the absolute value of the critical value, we reject the null hypothesis. This means we conclude that the time series is stationary. Asterisk if the ADF test statistic is less negative than the critical value, we fail to reject the null hypothesis. This means we cannot conclude that the time series is stationary. It may have a unit root. 3. Implementing the ADF test in stata. Stata has built-in commands to perform the ADF test. The primary command is dickey-fuller. Asterisk syntax asterisk. Asterisk variable, the name of the time series variable you want to test. Asterisk options, various options to control the test. The most important are asterisk no constant, suppresses the constant term, drift, in the test regression. Use this if you believe there's no drift. Asterisk trend, includes a time trend in the test regression. Use this if you suspect a trend. Asterisk lags, integer, specifies the number of lags of the first difference to include in the test regression, the p in the equations above. Choosing the appropriate number of lags is crucial. You can use information criteria like AIC or BIG to help you choose the lag length, more on this later. Asterisk level, specifies the significance level, alpha, for the test. The default is 5%, 0.05. You can set it to 1%, 0.01, or 10%, 0.10, etc. Asterisk regress, shows the regression table used in the DF test. Asterisk example 1, testing a series for a unit root, no trend or drift. First, let's create a simple non-stationary time series with a unit root. We'll simulate a random walk. In this example, asterisk clear all clears the memory. Asterisk set OBS 100 sets the number of observations to 100. Asterisk gen t equals underscore n creates a time variable. Asterisk gen e equals normal, 0, 1, generates a series of random numbers from a normal distribution with mean 0 and standard deviation 1, white noise. Asterisk gen y equals sum, e, creates the random walk which is non-stationary. Sum, creates a cumulative sum, which will have a unit root. Asterisk set t declares that the data is a time series with t as the time variable. This is essential before using time series commands. Asterisk dickey-fuller y, no constant lags, 2, runs the ADF test on the variable y without a constant term, and with 2 lagged first differences. Asterisk example 2, testing a series with a drift. Here, we've added a drift term, which represents a deterministic trend. The ADF test in this case includes a constant term to account for this drift. Asterisk example 3, testing a series with a trend. In this example, we include both a constant and a time trend in the ADF regression. Asterisk interpreting the output asterisk. The dickey-fuller command will produce output similar to this. Asterisk z, t, this is the ADF test statistic. asterisk 1% critical value, 5% critical value, 10% critical value, these are the critical values at different significance levels. Asterisk McKinnon approximate p-value, this is the p-value associated with the test statistic. In this case, the test statistic, minus 1.396, is less negative than all the critical values. The p-value is 0.5842, which is much greater than 0.05, the typical significance level. Therefore, we fail to reject the null hypothesis. We conclude that there is evidence of a unit root in the time series Y. 4. Choosing the number of lags. The choice of the number of lags, integer, in the ADF test is important. If you include too few lags, you might not adequately account for serial correlation in the errors, which can lead to an incorrect conclusion. If you include too many lags, you reduce the power of the test. Here are a few strategies for choosing the lag length. Asterisk information criteria, AIC, BIC. These are statistical measures that balance the goodness of fit of a model with its complexity, number of parameters. Lower values of AIC or BIC indicate a better model. You can use them to select the optimal lag length. Here's how. 1. Run the ADF test for a range of lag lengths, example from 0 to some maximum lag. 2. Store the AIC or BIC values for each lag length. 3. Choose the lag length that minimizes the AIC or BIC. Here's stata code to do this. Asterisk general to specific approach. Asterisk start with a relatively large number of lags and then successively reduce the number of lags, testing the significance of the last lag. If the last lag is not statistically significant, remove it and repeat the process. Asterisk rule of thumb. Asterisk some analysts use rules of thumb like p equals int 12 asterisk t/100 caret 1/4, where t is the number of observations. 5. Dealing with non-stationarity. If the ADF test indicates that your time series is non-stationary, you have a few options. Asterisk differencing. Asterisk take the first difference of the series, delta y underscore t equals y underscore t, y underscore t1. Sometimes, differencing once is enough to make the series stationary. If not, you might need to take second differences, the difference of the first differences. Asterisk log transformation. Asterisk if the series has exponential growth, taking the natural logarithm can sometimes stabilize the variance and make it stationary. Asterisk seasonal differencing. Asterisk if the series has seasonality, you can take seasonal differences, y underscore t, y underscore ts, where s is the length of the seasonal period, example 12 for monthly data. Asterisk detrending. Asterisk if the series has a deterministic trend, you can estimate a regression of the series on time and use the residuals from that regression in your time series model. 6. Practical considerations and common mistakes. Asterisk make sure the time series is properly defined. Asterisk that set command is crucial. Statin needs to know that your data is a time series and what the time variable is. Asterisk choose the appropriate model. Asterisk select the correct form of the ADF test, with or without a constant, with or without a trend, based on your understanding of the data. Asterisk select an appropriate lag length. Asterisk don't blindly use a default lag length. Use information criteria or other methods to choose an appropriate value. Asterisk be careful with differencing. Asterisk while differencing can make a series stationary, it also removes information. Overdifferencing can lead to problems. Asterisk consider alternative tests. Asterisk the ADF test is just one test for stationarity. Other tests, such as the Phillips-Perron, PP, test or the Kwiatkowski-Phillips-Schmidt-Shin, KPSS, test, might be more appropriate in some situations. 7. Complete stata example. Here's a more comprehensive example that combines many of the concepts we've discussed. In summary, the ADF test is a powerful tool for assessing the stationarity of time series data. By understanding the concepts, hypotheses, and implementation in stata, you can effectively use this test to build robust time series models. Remember to carefully consider the choice of lag length and the appropriate form of the test, with or without a constant/trend. Good luck.